Good morning, afternoon, or evening, depending on your time zone. I'm pleased to talk at this event launching the GEOTRACES IDP 2021, which is the culmination of so much hard work by the data collectors and the team involved in compiling and curating the dataset. So I want to start by acknowledging all of those colleagues. I'm going to discuss how we can go about extracting global scale process information from the GEOTRACES sections using data assimilating models. And the example I'll draw on is quantifying dust deposition from GEOTRACES aluminum data, work that was led by my graduate student, Hairong Xu. As you'll be aware, the GEOTRACES mission is to understand the exchange of trace elements across ocean boundaries and their internal cycling in the water column using a combination of sections and process studies. Sections map the distribution of trace elements across ocean basins, allowing us to identify regions and elements impacted by each process. Process studies, on the other hand, target specific regions to gather more detailed information about rates and mechanisms. The purpose of my talk is to demonstrate that synthesis and modeling of the section data can also be used to derive detailed process information and scale it up globally. The example I'm going to discuss is dust deposition, a key supply mechanism for micronutrients like iron to the surface ocean. While a number of GEOTRACES process studies have provided direct estimates of dust deposition at local scales, for large-scale estimates, we tend to rely on atmospheric models, which simulate the entrainment and transport of dust from desert regions, and ultimately predict its deposition rates on the ocean surface, like this example from the NASA GISS atmospheric chemistry model, which predicts that around 700 teragrams of dust reach the ocean every year, mostly in the Atlantic. Compiling predictions from multiple atmospheric models, 12 here, reveals that there's a lot of uncertainty in the rates and patterns of dust deposition, with some models predicting larger inputs in the Indian and Pacific Oceans relative to the Atlantic. As chemical oceanographers, we know that these different patterns and rates would leave unique signatures in the distributions of elements that dissolve from dust, such as aluminum, meaning that the IDP provides us with a powerful tool to discriminate between these estimates. Use of aluminum as a dust tracer dates back further than the GEOTRACES program to the seminal work by Chris Measures, in which aluminum was assumed to reside in the mixed layer for 5 years before its removal due to scavenging onto biogenic silica particles, allowing the dust supply to be estimated based on the source of soluble aluminum that's required to replace the mixed layer inventory every 5 years. To build on this approach, we need to consider additional processes that might impact mixed layer concentrations, including large-scale transport and vertical mixing of aluminum, which requires in turn more spatially resolved data that's only become available thanks to the GEOTRACES program. The GEOTRACES sections have revealed a dynamic aluminum cycle in subsurface waters that includes desorption of scavenged aluminum, which spreads the signal of dust deposition across depth, aluminum resuspension from seafloor sediments, and hydrothermal inputs at mid-ocean ridges. This leaves us with a whole suite of interconnected processes that need to be jointly constrained if we wish to extract information about dust deposition from the data. Our approach to that problem is to develop a global, three-dimensional model of the ocean aluminum cycle, in which all the different biogeochemical sources and sinks are simulated inside the OCIM data-constrained circulation model. Those biogeochemical processes need to be represented by sets of rules. For example, the aluminum source from dust deposition is represented as the product of a dust deposition rate, the mass fraction of aluminum in dust, and the solubility of aluminum. These rules contain a range of uncertain factors. For instance, we know that there's at least 12 different estimates of dust deposition from atmospheric models that we could select from. And while observations suggest that aluminum solubility scales with atmospheric dust loading, the parameters of that relationship are not well constrained. Our goal then is to allow the GeoTraces section data to guide us towards the inputs and parameters that allow our model to best explain the observed aluminum distribution. The data we used in this work comprises 11 GeoTraces sections, 8 of which were available in the previous IDP, shown in black, and 3 in the Pacific, which are newly added to the IDP 2021. Together, these sections cross some of the highest dust deposition regions in the global ocean and the lowest, and contain the signatures of aluminum resuspension from sediments and hydrothermal inputs. For a given pattern of dust deposition, and with some initial guesses for our uncertain parameters, our model will make a prediction about the aluminum distribution along each GeoTraces transect, which can then be compared to observations. For instance, here's a prediction of the aluminum distribution along the GAO2 section. From this starting point, we then employ a genetic algorithm to allow the model to learn from its mistakes and seek parameter sets that allow it to reproduce the observations more accurately, ultimately leading us towards an optimized model whose predictions are a lot more realistic. That optimization process is then repeated for each of the 12 different dust deposition estimates available to us, yielding an ensemble of 12 different optimized aluminum models. Some of those aluminum models are able to reproduce the observed aluminum distribution in all ocean basins quite accurately. This includes, for instance, the model that's supplied with the NASA GISS dust deposition estimate illustrated here, and as the black line in these 3 profile plots, which fit the red observations quite well. On the other hand, some members of the model ensemble, shown as the family of gray lines, cannot fit the data well, even after parameter optimization, and that yields useful information. It means that the patterns of dust deposition supplied to those models are simply not consistent with the dissolved aluminum distribution, no matter what parameters are selected. In general, the most unskillful models tend to be the ones that contain relatively high dust deposition estimates in the Indian and Pacific Oceans relative to the Atlantic, suggesting that that dust deposition pattern is less realistic. The model data fit for each ensemble member can then be used to identify the most likely estimate for aluminum inputs from dust deposition, which is shown here, and sums globally to 37 gigamoles per year, with the Atlantic contributing around twice as much as any other basin. We can also estimate a likely range for the global flux, which falls between 26 to 48 gigamoles of aluminum per year. An additional insight derived from our model is that in order to best explain the section data, the solubility of aluminum in the model needs to vary spatially by around an order of magnitude, between 10% in regions of lowest atmospheric dust loading, down to 1% in the regions of highest atmospheric dust loading, presumably reflecting different degrees of chemical processing in the atmosphere. Now, that relationship selected by our model agrees reasonably well with observation-based estimates, the colored lines, which are derived by leaching aluminum from aerosols, some of which were collected on the GeoTraces cruises themselves. I think this is a nice example of section data and process data coming together and telling us a consistent story. For other results of our study, I encourage you take a look at the paper published earlier this year in GBC. In summary, I've shown you briefly that combining aluminum sections with data assimilating models has allowed us to generate a new global estimate of dust deposition constrained by the GeoTraceS data product itself, which can then be transferred into other trace element work that requires large-scale dust deposition estimates, like ion cycle modeling. While I don't have time to list all the examples, I want to point out that similar methods to those I presented have been applied to constrain a range of other processes and elemental cycles. However, I feel like we've really only scratched the surface in terms of the information that we can mine from the IDP 2021 using this approach. One particularly exciting avenue is that for any process of interest, the IDP 2021 likely contains multiple useful traces, which can then be combined together into more robust multi-tracer approaches. For instance, aluminum can be combined with thorium isotopes and aerosol data in order to determine dust deposition rates that can jointly satisfy all of those constraints. Finally, if you found this interesting but think the methods I presented are beyond your own expertise, I want to point you towards the awesome OCIM tool developed by Seth John, which uses a simple graphical interface and was specifically designed to put some of these methods in the hands of non-modeling experts. And with that, I want to thank you very much for your time, and I look forward to the discussion.